My esteemed viewers, this video brings out a tutorial on transform and conquer method of algorithm design or transform and conquer strategy of algorithm design. That is, we talk about transformation as the name itself would imply, and this technique involves two stages. It's a two-stage procedure anyway. In the first stage, that is in the transformation stage, the problem's instance is modified in such a way, for one reason or the other, in such a way that the solution becomes very much easier. That is, the instance is amenable to an easy kind of solutions. Like any other design strategy, transform and conquer strategy comes with three versions. Number one, the instance is transformed into simpler form of the same instance. The problem remains the same, but anyway the input is modified in such a way that it becomes very simple to solve the problem. For example, the array is sorted. Okay, when array is sorted and many of the questions can be answered, you can find out the first top 10% and the last 10%. 10% of the students, or 10% of the population, or 10% of whatever, and it is very easy to find out which is the first biggest, second biggest, and third biggest, and fourth biggest in an array, and also the least valued element, the next least valued element, and the next least valued element. Okay, had the array been not sorted, it becomes it takes hell out of us to answer these kind of problems, and it is very easy to find out some of the statistical parameters if the array is sorted. And in set theory, many of the problems can be implemented if the array is sorted, because after all, array is a form of a set. Therefore, many of the questions can be answered if the instance is simplified. Of course, the problem remains the same. The second kind of version is, the second version in transform and conquer is, the presented problem, the instance of the problem is transformed into different representation. That is, if it is an array related problem, it is presented in the form of a tree, or if it is a tree related problem, it is presented in the form of a array. If it is a queue related problem, it can be represented into a stack, and vice versa. Like this, the problem appears with an instance shape and instance representation in a way, and upon transformation it will be converted. It will be converted into different forms, so that the procedure of getting the answer or obtaining the solution becomes a lot more easier. And the third version is, the transformation is a total transformation. That is, the instance of the problem is transformed into different problem. Of course, in the other two versions, the problem, nature of the problem remains the same, but here in the third version, the nature of the problem itself is different, and it is a total transformation. Let us say a problem running in sentences may be converted into a graph. A puzzle may be converted into a graph. Like this, there is a total transformation for the given problem, and we will draw the algorithms related to different problem representation, or the transformed problem into a different problem, and the related algorithm will be drawn from the cupboard, and it will be applied and it will be solved. Okay, this is the third version, and we will take up examples for all the three versions. Okay, and in this video we will have the first kind of the version. That is, this first kind is called as the instance simplification. The first kind is called as instance simplification, and the second kind is called as the representational change, and the third kind is called as the problem reduction. I repeat, this is called as instance simplification. This is instance simplification. Okay, this kind of transformation is called as instance simplification, and this is representational change. This is entire thing will be represented in a different form, but the problem remains the same. The nature of the problem remains the same. But here it is a total change. A problem of one kind is reduced to problem of other kind. Therefore, this particular version is called as problem reduction. Next, we will go for the next slide. Yeah, first problem that we take up as an example is element uniqueness problem. Okay, element uniqueness problem. We had done this, we had attempted this in our when we discussed on brute force technique. Let us say brute force technique involves too much of comparison. Let us say if the elements are 5, 7, 2, 1, okay, and this is a unique array anyway, there is no doubt about it. But the brute force way is we will consider this again, okay, 5, 2, 1. The 5, the first element will be compared with the 3 other elements, okay. It will prove to be different, and 7 will be compared with the remaining 2 elements, okay, and 2 will be compared with the last element, okay, and the last element will come pure. Anyway, it needed 2 for loops, one to let out each and every element for the comparison, the second for loop for comparison. Therefore, the complexity involved, okay, this kind of a brute force method way of finding uniqueness of an array fell into, if you recall your attention, big theta of n square. So it was a quadratic complexity. Now, if you sort the array, for example, the same thing, if it is put this way, 1, 2, 5 and 7, okay, it becomes lot more simpler. Okay, this is to be compared with this, and this is to be compared with this, this is to be compared with this. There are 4 elements and 3 comparisons. If there are n elements, there will be n minus 1 comparisons. In any of the iteration, if two neighboring elements are equal or identical, then the algorithm would stop and it will convey the message. Okay, this is a lot more simpler method. Okay, and it becomes linear, as you could have guessed. So we will write the algorithm. Algorithm is here available. Okay, what it does, it finds out whether or not the array presented is unique, that is, it contains all the elements to be unique. Okay, input is an array which is not sorted. The output is whether the array contains unique elements or not. It doesn't contain any unique element, and there are few elements which are identical in nature. Okay, it will return either true or false. Okay, sort the array in ascending order. This is to be done first. Using best of the sorting algorithms with a lower complexity. Of course, for I equal to 0 to n minus 2, because you had seen there will be only n minus 1 comparisons. Okay, since 2 is involved over here, we have to go up to n minus 2. If a of I, the preceding element, is equal to the next element, a of I plus 1, then return false. Okay, if all the comparison happens, then definitely it should be unique element. It should be containing unique element. At no stage this particular let us say condition came true. Therefore we can analyze the complexity of this very simply. Okay, in the worst case, number of comparisons for presort uniqueness element is, okay, presort method way of finding uniqueness of an element is, okay, the time consumed for sorting, okay, using best of the algorithms, of course, okay, as a function of input size n plus number of comparisons over here, it is definitely n minus 1, and this is, we will have big theta of, this is equal to, let us say, big theta of n log n. We have used best of the algorithm, n log n, and plus this is big theta of n. Therefore, among these two terms, this is the highest term, or this is the term with bigger complexity. Therefore, presort element uniqueness problem belongs to the efficiency case of big theta of n log n. Okay, this is the advantage of having transformed the given array in a particular arrangement, either ascending order or descending order. Okay. Next problem that we are going to consider is the finding mode in an array. Mode is a statistical feature of a list available in a list. It only represents an element which frequently repeats, which has more frequency of repetition. Okay, we will take an example. First of all, we will identify the method. We will identify the logic. We will explain the logic. Of course, this is a method on transform and conquer. So there is 2 7 7 7. There 7 repeats 3 times. Then comes 8. Let us say. Okay, it's an arbitrary example anyway. Okay, 9 comes another one is 9. Then comes 15. 4 15s. Let us say 15. Yeah. 15 and another 15, then comes, let us say, 23. Okay, here the mode value is 15 and the frequency of its repetition is 4, and 7 cannot be a mode because 7 has only the frequency equal to 3, and while 15 has frequency of 15. And it is very important to remember that this modal value or mode may repeat anywhere within the array. Okay, unlike other central tendency features that we present usually, that is the mean and the median, the modal value can come anywhere in the array. Therefore, the procedure involves you sort the array first. Okay, it becomes a hell lot difficult if you think of making a algorithm on a unsorted array. Okay, we have indices as usual. There is I, okay, index, which moves in this fashion, which moves from left to right. So it has a limit of moving from 0 to n minus 1, and we will carry another let us say another index, say by name frequency mode. Okay, modal frequency, or anyway, okay, frequency of the mode. To start with, it will be 0. Okay, when it comes over here, it will become 1. And we will have another 2 variables. One is run value. Let us say run value, the value over which an index is running, run value. So here run value is 2, and run length is another one. Okay, so with these 3 variables, yeah, the algorithm will simply work on a sorted array. Of course, run value, when it comes over here, okay, it will become equal to 7. Okay, and this run value continues for 3 times. Run length is 3. Here run value is 1, run length is 1, frequency is 1. Then when it jumps over here, frequency, when it completes the comparison, here till here, the frequency, the run value becomes 7, run length will be 3, and run length will be compared with the frequency value gathered earlier in the earlier iteration. So in this case, frequency is 1, and now run length is 3, therefore run length is greater than this frequency value, or frequency value gathered before in the previous iteration is 1 and run length here is 3, therefore frequency will achieve a value of 3. I will be stationed in 0 first, and then it gathers I plus run length, I plus run length, I plus run length. Okay, till here it comes just moving laterally, and it makes a jump. I makes a jump over here. Okay, I is set to 0. When I points over here, when it gathers all the 3, it will make a jump. It becomes I plus 3 or I plus run length. Then it will be set to this. Here there is a difference between this and this. So the frequency value changes. Frequency value will once again become 1. The previous gathered frequency is 3. Okay, run length here becomes 1. The previously gathered frequency value will become equal to 3. Therefore that is greater. Therefore that will remain. And once again it will come to 9. Okay, by this time I will also have moved at this particular point. Okay, I will always move along with run length. Okay, it is I plus run length. Sometimes it makes a long jump, sometimes it will move just by one element. When it comes over here, run length will be equal to 1 again, run value will be equal to 9, and the previous gathered frequency is 3, and now run length is 1, therefore frequency of 3 will remain. When it comes over here, run length is 1, 2, 3, 4. Till here, whatever that I has gathered, and when it comes over here, it is I plus run length. Okay, now run length becomes equal to 4. The previously gathered frequencies was equal to 3. Therefore, 4 is greater than 3. Current run length is greater than the earlier stored frequency value. Therefore, frequency value will change. Frequency value will become equal to 4, and run value will be equal to 15. Okay, run value will be keep changing. Okay, whenever it remains the same, it continues as it is. When it becomes different, run value over here becomes 8, run value will become 9 over here, run value will turn into 15 over here. Okay, that's how the comparison goes on. The ease with which the problem is solved lies in the sorting of the array. We sorted the array, therefore all equal valued elements came together and they sat side by side. Now the searching becomes very easy, the counting becomes very easy, finding the modal value will also become very easy. Okay, so we will go for the algorithm now. We'll try to understand the algorithm now. Okay, right. Right, algorithm is here. Okay, we will go slowly. Algorithm presort mode. Array is presented. What it does? It finds out the mode. It finds the mode. Okay, it finds the mode by sorting first. The input is an array which is not sorted. The output is the modal value, or the mode, or the element which repeats more frequently in the given array. Okay, I is set to 0 because this is the starting position of the index. You can recall the earlier picture that we drew in the previous slide. Okay, I equal to 0, the starting position of the index. Frequency mode equal to 0 because we have not yet gathered anything, therefore it is set to 0. Now we will set the bounds. While I less than or equal to n minus 1, as I told you, as it was mentioned, I can start from 0 to n minus 1. It can go up to n minus 1. Okay, while I lesser than or equal to n minus 1, do run length equal to 1. Okay, the first iteration started, let us assume run length equal to 1, because anyway this will be poking to any one of the elements. It must be 1. It cannot be 0. At least it repeats one time. So run value equal to a of I, whatever that is there in that particular position will be taken as run value. Now comparison starts. While I plus run length is lesser than or equal to n minus 1. Okay, if there is only one element, okay, which is not repeated, it will become 0 plus 1. Okay, so 0 plus 1, it is not lesser than n minus 1, and a of I plus run length is equal to run value, then only run length is to be incremented. Okay, if the I has not crossed its limits, this is the meaning of this, and as the run length moves along with the I, okay, therefore a of I plus run length, if it is equal to run value, then run length will be incremented by 1. Okay, so at the end of at the completion of this, see this control, this while control should break its control if any of the conditions becomes untrue, or I will have reached the destiny, that is the last position. Okay, in between it breaks due to this. Okay, this is the culprit. This becomes not equal to a run value, therefore it breaks and it comes over here. Okay, as soon as the condition is broken, as soon as the control comes over here, okay, upon not satisfying both the conditions, okay, and then it will bring along with it some value of the run length. Let us say as far as 7 is concerned, okay, the run length was 3, okay, 7 was the first element which repeated for 3 times. Anyway, if you recall your attention for the previous slide, if run length was 3 is greater than frequency mode was 1, because the first element has only one element of that kind. Okay, therefore frequency mode will be changed to run length. So frequency mode becomes 3 and mode value becomes run value. Mode value will become run value. Then we will increment I equal to I plus run length. Okay, I will be jumping by 3. Okay, and then similar thing, it will continue till the array ceases to exist. Okay, till when I reaches its limit, then we will return mode value. Okay, for this example the mode value will be 15 because it carried the frequency, the run length equal to 4, therefore frequency of the mode is also equal to 4 and mode value that's being 15. Okay, right. We will take another example. Find the distance between two closest numbers. The two closest numbers. In an array, of course. Okay, the two closest numbers is nothing but ai, okay, ai, okay, minus ai plus 1. The numerical difference between the values of the neighboring elements and its absolute value is called as distance between the numbers. And we need to find the pairs of elements which will possess the least possible value of the difference. Therefore, if we arrange the array in order, let us say 15, okay, in ascending order, 17, 19, say 22 and 37, we will find the difference between these two. So one comparison, and distance between these two, distance between these two, distance between these two. So 1, 2, 3, 4. Okay, for 5 elements we need to compare, we need to find the differences between that is 5 times, that is 4 times, 5 elements 4 times we need to find the difference. Therefore for n elements we need to find n minus 1 differences, and among the differences we need to pick up the least value. Okay, the least value of the difference, we need to pick up the least value among the differences. Now we will write the algorithm closest pair. An array is given to this algorithm. Now sort the array in ascending order. We have to do this. This is the transformation that we want to bring. And here closest equal to a of 0 minus a of 1. This is the first value that we want to pick up, because we need to compare this closest with the next upcoming closest value. Okay, closest value, it is an absolute value, of course, a of 0 minus a of 1. Now for loop starts. Okay, since one of the differences is already taken, it has to move from 1 to n minus 2 of course lesser than n minus 1. Since 2 is used, it should be n minus 2. So for I equal to 1 to n minus 2, what we have to do, if a of I, that is a of 1 minus a of 2 is lesser than the closest, then closest will be equal to a of I minus a of I plus 1. Okay, I repeat, if a of I, that is a of 1 minus a of 2 is lesser than the closest, assumed closest, then closest will be definitely equal to a of I minus a of I plus 1. Okay, and if this is lesser than this, this will only remain as the closest pair. Like that, every element, every pair of neighboring elements will be compared. The difference is sort, and the differences is compared with the earlier difference, and the least possible value of the numerical difference is taken, and those two variables will be declared as, and that is the closest distance. That is the closest distance between those two elements. Okay, and this, as you can see has a complexity that is needed to sort the array itself. In the previous case also, the complexity of mode is, okay, we will just estimate this anyway for the sake of clarity and for the sake of completeness. So therefore, time consumed, okay, in finding the mode for an array as a function of n number of elements is equal to time required for sorting, okay, for the same array of n dimensions plus this comparison. Okay, this comparison, anyway it has to run for n number of times, n minus 1 number of times, let us say. Therefore, this we will have used, okay, one of the finest sorting algorithms. Therefore, this is n log n, theta n log n, and this is big theta of n, Among these two terms, this is the biggest term or the significant term or the largest term. Therefore, okay, the time consumed in finding pre-sort mode or mode of an array, mode of a sorted array, happens to be big theta of n log n. Okay, this is how the complexity is to be analyzed. Okay, the simplification method we adopted, and the complexity of that simplification procedure, and here simplification procedure is simple sorting, that is the way. Okay, this is explained, and even this also comes with a complexity, linear complexity, as you could have wished. Okay, I will leave it to the viewers, my respected viewers, and they will be able to do this. Okay, you need to put sigma and you need to find out, but that's not required. Anyway, this will also come out to be a complexity of the sorting algorithm that we might have used. Therefore, this also belongs to big theta of n log n. Okay, find the intersection of two sets A and B with m and n elements respectively. Okay, it would have been very tough, okay, had the array is not sorted, okay, had the transform and conquer technique has not been applied, because it becomes quadratic complexity. We need to let each and every element from one array compare with all the elements in the other array, okay, and pick up only the first element that is let out for comparison is there present in the other array, because it becomes a common element. Like this, every element in array is to be compared with the every other element in another array, okay, for the possibility of its presence in another array. If it is present, it should be included in some other array called C, which forms the intersection of A and B. But our transform and conquer method paves a very easy way for solving this problem too. Okay, we need to sort the array A in ascending order using the best of the algorithms, and we need to let us say we will sort only A in ascending order, and we will perform binary search on array A, okay, with keys as B's elements. Okay, we will draw one after the other the elements from B, and then we will apply the binary search on A. If it is present, if the elements of B is present in A, it will be included in another array called as C. So this becomes very simple. So therefore, the complexity of this algorithm is okay, let us say the complexity, the time consumed for A intersection B equal to the complexity for sorting, that is n log n, okay, and complexity for binary search, okay, that is log n. Applied, log n applied maybe n times, or it's better we select that array and we will arrange the array which has least elements. If let us assume that here n should be taken as Okay, I will change this to be S. Let us say S should be taken as the minimum among M and N. Okay, it's a minimum value among M and N, M comma N. Okay, therefore what we do is we will arrange that array which has minimum number of elements. Okay, because both of them are coming with M and N elements, we don't know whether M is small or N is small. We will find out which is the smallest number of elements, then we will arrange that in ascending order, then we will use the B's elements to be keys and we will search in the array, and number of searching will also becomes very simple, and very length, as far as length is also concerned, it becomes very small. Then find the median in a list containing n element array, containing n elements. Okay, how to find the median? Once you sort the array, the key, the element that is present exactly in the center is called as the median. Okay, I repeat, in an array, in a sorted list, the element which is present exactly at the center is the mean. Okay, and if it is 9 by 2 will be 4.5. Since it is ceiling, the fifth element will become median, and if it is 7, then it is 7 by 2, it is the fourth element. If it is 8, it will be 8 by 2, ceiling value. It is very simple because the array is arranged in order. Okay, sort the array A in ascending order and return A of ceiling of n by 2 as the median value. It is so simple. Therefore the complexity should be, if you just think it over, okay, the complexity of this algorithm as a function of input size is the complexity involved, that is big theta, okay, big theta n log n, just for sorting, okay. Say quick sort algorithm you must have pressed into service, and here there is only one comparison. Okay, it's a constant case complexity, let us say theta of 1. Therefore finding a median in a sorted array falls under big theta of n log n. So this is the advantage of having thought our solution process on lines of transform and conquer. Okay, so in this session we dealt with how simple some of the problems will be if an array is sorted. Okay, and we can venture in finding at least the first biggest, second biggest and third biggest in a unsorted array. Then definitely it's a realization as to how things will become. So searching becomes easy when the array is sorted, and finding the top 10% becomes very easy, finding the bottom 10% becomes very easy. Okay, finding the first, second and third and fourth toppers in a class becomes very easy. Okay, it's also very easy to become which is the least marks obtained in a particular subject, the next least and next least. Okay, had the array not been sorted, had the instance not been transformed, okay, it would have taken a lot of time of the computer, and our algorithm would have gone verbose, and our algorithm would have gone more complex. Therefore this is a few simple examples. Okay, this tutorial carried very few simple examples which are based on the first version of transform and conquer, that is instance simplifications. Instance appeared in an unsorted way, carrying a problem along with it, maybe finding the biggest or the smallest or whatever, we sorted it. That was the transformation, but the problem remained the same. It may be finding the mode, it may be finding the median, it may be finding the first 10%. Okay, so with this we will close this session. Okay, and we will take up tree related problems, okay, under transform and conquer category. Until then, bye.